Queens and kings of physical computing, it's Prof. Gene. In this lesson, we'll take the Raspberry Pi Pico for a spin using a potentiometer. A potentiometer is an analog input device, usually a knob, but there are other kinds as well. In a prior lesson, we used this knob-style potentiometer with the Circuit Playground Bluefruit. We'll now hook this bad boy up to a Raspberry Pi Pico. And in case you have one of these far more common, inexpensive plastic potentiometers, you'll often find these in intro electronics kits. I'll show you how you can use one of these as well. The concepts are very similar. Now we'll first show how to use CircuitPython to read values from the potentiometer, and then we'll have a challenge and show the solution to turn the individual LEDs in our light strip on or off based on readings from the potentiometer. And even if you complete the challenge, you should stick around and check out the solution I'll demonstrate, because I'll also show how you can use the Python concept of slices to quickly update LED lights on a strip without having to use any for loops at all. Let's spin up some big learning. So my students have one of these potentiometers that's on a breakout board, and they also have this 3-clip cable for easy hookup, but you can hook up one of these inexpensive plastic potentiometers common in many intro electronic kits too. All you'll need is 3 jumper wires. I'll show you how to do that in just a bit. Now these 2 potentiometers have knobs, but there are lots of other kinds of potentiometers as well. For example, my students also have 3 slider potentiometers. They're also connected via the same 3-wire setup, power, ground, and signal. We'll use those in a future lesson. Now here are the wiring diagrams for either of the knob potentiometers I just showed. Anytime you use a potentiometer, you've got 3 wires, power, signal, and ground. And when choosing a signal pin, make absolutely sure that you're choosing a pin that supports analog input. On the Pico boards, the analog pins are GP26 through GP28. You can also refer to them by the names A0 through A2. For power, make sure that you use the 3.3V out pin. The other pins will provide more power, and that's going to result in inaccurate readings at the high end of the scale. And here's a quick look at how things are set up with one of these inexpensive plastic potentiometers. Now if I take this off of the breadboard, you see that there are 3 legs. The left one is what I attach to ground, the middle to signal, the right to power. By the way, here's something you can try on your own. On these types of potentiometers, the middle pin is always the signal pin, but if you flip the ground and the power wires, you'll get readings in the opposite direction. So the location on the dial that used to be high is now low, and vice versa. And here's the setup of the potentiometer breakout board. The jumper wires are heading into the same locations on the breadboard, but the other ends of the jumper wire are alligator clipped to the potentiometer. Now to code things up, this is familiar to you if you used potentiometers in our earlier video with the Circuit Playground Bluefruit. We import analog in from analog I/O, then we create an analog in object. I'm calling mine potentiometer, a good name for a potentiometer. Mine is connected to pin A0, which is the same as pin GP26 on the Pico. You can use either name if you'd like. And then down here, we'll simply put the reading returned from the potentiometer's value property into a tuple. Then we'll print that so that we can view the number in the serial console, and we can also view the plotted output in the moo plotter. And I'll add a 1/4 second time sleep delay just so that the speed of the board output doesn't overwhelm the slower printing and plotting. So let's code. So here's our potentiometers code. We'll import from board and time, and also from analog I/O, we'll import analog in. Then we'll create our analog in object. We're going to call that potentiometer, setting that equal to capital A analog capital I in. I'll pass in board.A0 since that's where my signal pin is attached to. I could have also called this board.GP26. Either name would work. Some pins have multiple names, sort of like some wrappers. And then in while true, just a reminder, the potentiometer is going to return a value from 0 to 65,535. And then inside the print statement with 2 parentheses, we'll say potentiometer.value, comma, and we'll close with 2 parentheses. This puts it in a tuple so that we can plot it as well as print it. And just to make sure that we can see this output, we'll time.sleep, and in parentheses, we'll pass in 0.25 to wait a 1/4 second. Then let's open the serial console, and we'll save this to our CircuitPy volume as code.py. Let's also open the plotter and adjust the windows. And look at this, as I turn things, I start off and I'm down at the low end of the potentiometer knob, but as I turn clockwise, I can see the numbers are getting larger and larger until I'm up around 65,000. I can go back down, I can move this in both directions. My potentiometer readings are working fine. Another scale down, good work. Now it's time for a challenge. Now the challenge is going to use a potentiometer and a NeoPixel strip, so I'll keep the potentiometer wiring the same, and I'll wire the NeoPixel strip to V-bus power with the signal to GP16. That's this pin here in the lower left. So in this challenge, you'll modify your code so that as you turn the potentiometer, you light up the LEDs on your NeoPixel light strip. So turn to the far left counterclockwise and you shouldn't see any lights. Turn to the far right or clockwise and you should see all of the lights light up. And you should progressively turn the lights on or off as you rotate the potentiometer knob in either direction. The video on the right is showing you how things should look when things are done, so why don't you give this a shot. Pause. I know you can do it. And when you're ready, resume, and we'll compare answers. So this is going to be code for potentiometers and our NeoPixel strip, and we need to import NeoPixel since we're working with our NeoPixels. And let's define the values we'll use to create our strip object. So I'll start with strip_pin equals board.gp16. If you're using a different signal pin for your LED strip, make sure that you change that here. Then strip_num of lights equals 30. I happen to have 30 LEDs on my NeoPixel strip. And then I'm going to call my object strip, set that equal to NeoPixels.N Neo_P pixels, and in parentheses I'm going to pass in strip_pin, comma, strip num of lights. Then down in the while true loop, we need to convert a potentiometer reading, which is 0 to 65,535, to the number of LEDs we want to turn blue, which is a number in the range from 0 to 29. Now I could do all the math on one line, but to make it easier to read, I'll do it on 2 lines. So first I'm going to convert the potentiometer reading to a value from 0 to 1. So we'll name the value holding the number of LEDs we want to light up as simply LEDs_2_light. And initially this is going to be a value from 0 to 1, and I'm going to create that by dividing potentiometer.value by 65,535. So now we've scaled that potentiometer reading from 0 to 1. But now we want to scale this value back up to a value from 0 to the number of lights on our strip minus 1. The minus 1 is there because we might be lighting up lights at index value from 0 to 29, not 0 to 30. Remember, we're 0 indexed. So on this line, we just say LEDs_2_light equals LEDs_2_light multiplied by, and in parentheses, strip num of lights minus 1. Don't forget the parens or the multiplication will happen first. Now this will scale our value to a number from 0 to 29, which is great, but we're going to have decimals in here. What we need to do is round this to the nearest whole number because there aren't any fractional LED values. The indices are all whole numbers or integers. And if we don't round this, we're going to get an error. To round this to the nearest whole number is super easy. I'll just surround this whole equation in parens and put the keyword round in front of it. And let me get rid of this print and time sleep down here for now. And while I could use a for loop to turn our group of lights on or off, I want to show you a new technique called slices. And slices work really well with LED values. Now before I show you slices, first I'm going to look for the case where there are no LEDs to light up, and if so, I'm going to turn all of my strip black. So here I'll say if LEDs to light double equals 0, then I'll strip.fill, and I haven't defined any colors yet. So I'll do that below where I set up my strip. I'll say all caps black equals the tuple, so parens 0, 0, 0, and blue all caps equals the tuple, so parens 0, 0, 255, and then I can set my strip.fill to black if LEDs to light equals 0. Else, and here's where we can use Python slices for LEDs. So the first thing I want to do is to light up lights 0 through LEDs to light minus 1 in the color blue. Now remember, it's minus 1 because we're 0 indexed. So to do this on one line using slices, I can take a slice or a portion of an indexed collection. Now our strip has indices because we can refer to strip in brackets 0, strip in brackets 1. Well, if we say strip square bracket 0, LEDs to light, then close square bracket, this will allow us to update all at once all of the indices values from 0 up to but not reaching LEDs to light, which is great for us because we want to stop at LEDs to light minus 1 because we're 0 indexed. So how do we make this all blue? We say equals blue. But to make that color tuple blue repeat for each of the indices, we need to specify how many times to repeat blue, so we just multiply this by LEDs to light. So this takes our strip, and it's going to light up lights 0 up to but not including LEDs to light. So it's going to go from 0 to LEDs to light minus 1, and it's going to set these equal to blue. But to get blue in all of those lights, we need to multiply blue by the LEDs to light. That just repeats blue across all of these indices. So if LEDs to light is 5, we'll go from indices 0 to 4. We'll take blue times 5, and that's going to put 5 copies of blue starting at index 0 and ending at index 4. Nice. The syntax is a little odd, but it's super efficient once you get used to it, and we don't even need to use a loop, which is very cool. Now we'll use a slice to turn off the remaining lights, and just to make this a little bit easier to read, I'm going to first calculate how many lights need to be black. So I'm going to call this num of black lights, setting this equal to strip num of lights, which is how many lights there are on the strip, which is 30, minus LEDs to light, which is the number of LEDs that we just lit up. So then we can create our slice like this. Strip, brackets, LEDs to light that starts at 1 after the last LED we lit up because we were 0 indexed, colon, strip num of lights, which ends the slice at strip num of lights minus 1. And then we set this equal to black times num of black lights. And I'll shrink this down, so we've just updated our sequence of NeoPixel LEDs without having to write a single for loop. Groovy. And now, just so we can see how many LEDs we should be lighting up as we turn the potentiometer, I'll add a print statement outdented to the same level as if and else, and I'll say print F double quotes, and inside the double quotes, LEDs to light, curlies, passing in LEDs to light, and we'll time sleep 0.2 to slow things down a bit, and then we'll save and open the serial console, and I'm not seeing any errors in here. Looks like we're running. I'm starting with my potentiometer turned all the way to left, and let's turn that pot. So we start at 0 lights, and we turn to increase the lights, but when we crank things all the way up, ho, that last light isn't lit. Can you guess why? Look at this guy. Light number 29 is off. Well, the reason for this is that we calculated a range of 30 because we have 30 lights to turn on, which is correct, but there is a 31st condition, which is actually the first condition. When we get a value of 0, we should turn off all the lights. Oh yeah, tricky. So we need a range of lights that's actually one more than the number of lights we want to light up so that we can accommodate the case of no lights as well. That means that we have to calculate our range as 31, not 30, so that's 0 plus lights 1 through 30, or those lights are indexed at 0 through 29. So let's quickly modify the code. So the change is super easy. When we calculate up here LEDs to light, we don't want to subtract 1 from strip num of lights. We want to leave strip num of lights in there. This will give us a value from 0 to 30, which will let us light up from 0 to 30 lights. I'll also make the change in the comment, and I'll remind us down below that there are 31 conditions, 0 all off, plus 30 lights. Now let me save this, open the serial console, let's take a look at what we got. So we're cranked up to full, and look at that, we got 30 lights. Sweetness! All of them are there, turn them all off, turn them all on. These are looking great. Why don't we go and get rid of the print and the time sleep at the end and see if we can speed things up a bit, and we'll save. And let's crank that potentiometer. Oh, look at how smoothly that scrolls. All the way off, all the way on. We got all 30 lights working here. Another skill in the bag, Circuit Pythonista. We hooked a potentiometer up to the Raspberry Pi Pico, and for my students who'd already started with the Circuit Playground Bluefruit, that part might have been easy, but we also threw slices in there, so we got another really fast, really efficient Python skill. Go make more things glow with that special superpower you just acquired, and continue to make something awesome.